Welcome to this lecture on electrical network protections. Now we look at the inputs and outputs ports on the protection relays. Input and output ports enable data exchange between a relay and external devices. There are four main types of signals exchange. First are binary inputs, and binary inputs receive signals from other protection devices connections to the same protection object. Typical examples include transformer gas protection and pressure protection signals. Second, output indicator contacts. These contacts operate when the protection trips or whether the protection fault is detected. They provide status information to control and monitoring systems. Third, trip output contacts. These contacts send the trip commands to circuit breakers. They are responsible for disconnecting the protection elements from the power system. Fourth, LED indicators. LEDs provide local visual information about protection operation or detected faults. They help operators quickly assess relay status. Both indicator contacts and trip contacts are electromechanical. This ensures reliable operation and clear galvanic separation from the control circuits. Together, input and output ports form a physical interface. This ensures reliable operation and clear galvanic separation from control circuits. Together, inputs and outputs ports form a physical interface between the protection relay and substation and the power systems. Now we summarize the advantages of microprocessor-based protection compared to traditional relays. A key advantage is flexibility. The same hardware, a single protection terminal can perform different protection functions by changing software. There is no need to replace physical relays. One protection relay can store multiple settings groups. Typically, up to 4 setting groups are available. You activate them locally or remotely, depending on the operating condition. Remote settings and controls are standard features. This enables faster adaptation to network changes and operational requirements. Microprocessor-based protection offers much higher performance. Sensitivity, operating speed, and accuracy are significantly better than the traditional relays. Measured quantities can be represented as mathematical functions with multiple parameters. These allow precise modeling for protection characteristics. Protection functions support multiple time delays and speed stages. Both fast and delayed tripping can be implemented in the same device. Modern relays continuously monitor their own condition. Self-supervision detects internal faults and increases reliability. Physical advantages are also important. Microprocessor relays have much smaller size. They require far less wiring than traditional relay panels. Finally, the same protection hardware can perform control and automation tasks. This includes switching operation, interlocking, alarms, and monitoring. Together, these advantages explain why microprocessor-based protection has largely replaced traditional relays. Now we introduce measuring transformers. Measuring transformers convert primary current and voltages to levels suitable for measurements, protection, and control devices. Their role are fundamental in power system. Measuring transformers have four main tasks. First, scaling. They reduce primary current and voltage to standardized secondary values used by relays and meters. Second, electrical isolation. They separate the primary circuit from the secondary circuit. This protects personnel and sensitive equipment. Third, overload protection of measuring devices. They prevent excessive current and voltage from damaging protection and measurement instruments. And fourth, installation flexibility. They allow protection control and monitoring devices to be installed at a safe distance from high voltage primary equipment. Current transformers reduce line current to typical secondary values, such as 1 amp or 5 amps. Voltage transformers reduce primary voltage to standard secondary levels, commonly 100 volts. Without measuring transformers, modern protection system could not operate accurately. Now we look at current and voltage measuring transformers in more detail. Measuring transformers divide into current transformers and voltage transformers. The most widely used are current transformers and voltage transformers. Current transformers divide by purpose into measuring current transformers and protection transformers. The difference lies mainly in magnetic behavior. Measuring current transformers must be accurate near rated currents. They are designed to operate correctly only around nominal currents. Protection current transformers must transmit large abnormal currents accurately. They must remain unusable during the faults. Because of this, their ferromagnetic core characteristics differ. Accuracy of measuring current transformers is defined by current and phase angle errors. In energy metering, accuracy class must be not worse than 0.5. This means current error must be stay below 0.5%. Phase angle error must stay below 30 minutes. Protection current transformers face different challenges. The main problem is error increase during high voltage currents. This happens due to core saturation and periodic DC components in short circuit currents. These effects cause additional magnetization of the core and loss of accuracy. Protection current transformers use accuracy class such as 5P and 10P. The letter P indicates protection application. Another important aspect of the current transformer operating safety. A current transformer normally operates close to short circuit conditions on the secondary side. If the secondary circuit opens, the transformer enters no load operation. This is dangerous. In that case, very high voltage appear on the secondary terminals. Voltage can reach tens of kilowatts. The core heats strongly, up to dozens or even 100 times normal losses. For this reason, the secondary circuit of the current transformer must never be opened under load. As an alternative to conventional current transformers, Rogowski coils are used. A Rogowski coil is an air-core toroidal winding placed symmetrically around the conductor. The conductor feeds through the center of the toroid. Because it has no iron core, there is no saturation, it is safe under high currents. It is suitable for measuring large volt currents. Finally, well-known examples of modern measuring transformers include combined current and volt transformers used in the compact substations. Next, we'll look at the voltage transformers and modern measuring sensors. Voltage transformers are divided into measuring voltage transformers and protection transformers. A voltage transformer normally operates close to no load conditions. For this reason, a short circuit of the secondary side is dangerous. If the secondary circuit is shorted, very high current follows. Then transformer core and windings heat up. Damage can occur quickly. At higher voltage levels, voltage measurement is often based on voltage dividers. Two main dividers types are used. Firstly, capacitive voltage dividers. These are widely used in high voltage systems. Capacitive voltage transformers are built using series connected capacitors and electromagnetic transformers. Second, resistive voltage dividers. These use active resistance elements and are applied in specific measurement and protection tasks. Protection voltage transformers have defined accuracy classes. Typical protection accuracy classes are 3P and 6P. Now we move to modern sensor-based measurement technology. Microprocessor-based protection and measurement devices require very low input power. These enable the use of sensors without magnetic cores. These sensors measure current and voltage without iron cores. As a result, there is no magnetic saturation. Measurement remains linear even very high currents. Because saturation doesn't occur, there is no need to consider sensor error during large fault currents. However, this also removes an important protective feature. Traditional transformers limit secondary current during faults to a core saturation. Coreless sensors do not provide this limitation. As a result, measurement device must include additional protection against overcurrents. Understanding these differences is essential when selecting voltage transformers or modern sensors at the protection application. Now we look at optical sensors used in protection and measurement. In addition to conventional transformers, modern systems use light-based sensors known as optical sensors. Those sensors can operate as both current and sensors and voltage sensors. The sensing element is an optical sensor is a crystal without a center of symmetry. Its optical properties change under the influence of electrical or magnetic fields. First, voltage optical sensors. Those sensors are based on the coils effect. When the electrical field is applied to the crystal, the refraction index of the crystal changes proportionally to the field strength. This change affects the polarization of the light passing through the crystal. By measuring this change, the application voltage can be determined. Second, current optical sensors. Current sensors are based on the Faraday effect. Here the magnetic field created by the current flow causes a rotation of the light polarization plane. The rotation angle is proportional to the magnetic field strength and therefore to the currents. In both sensor types, light is transmitted through the optical fibers. The typical structure includes a light source, usually a light-emitting diode, an electrical path or fiber, a crystal acting as a sensor element, a polarizer, a photodiode as a light receiver, electrical signal processing. Optical sensors offer several advantages: complete electrical isolation, no magnetic saturation, high accuracy over wide measurement range, immunity to electromagnetic interference. Because of these properties, optical sensors are increasingly used in modern digital substation and protection systems. Now we focus on the protection device used in medium voltage networks. In the medium voltage system, two main protection devices are used: fuses and protection relays. Medium voltage fuses operate on the same basic principle as low voltage fuses. Their operation depends on the current magnitude and time. The key requirement is correct selection. The fuse characteristics must match the protection object. Typical protected objects include transformers, motors, capacitor banks. Each of these has different starting current and overload behavior and the fault characteristic. The fuse must withstand normal operating condition but operate reliable during faults. This figure shows a complete set of medium voltage fuses from a single manufacturer. Different fuse types are designed for transformer protection, motor protection, and combined transformer, motor, and capacity protection, and the voltage transformer protection. Unlike fuses protection, relays do not interrupt the current path directly. A protection relay operates by issuing a trip signal. This signal is sent to the switching device. The switching device, such as a circuit breaker or load switch, then opens and interrupts the currents. This separation of function is important. The relay detects and decides, the switching device interrupts the circuit. This principle applies to most modern medium voltage protection schemes. Now we focus on overcurrent protection. Overcurrent protection has a central role in electrical network. In distribution networks, the main overcurrent protection elements are fuses, circuit breakers, protection relays. Circuit breakers are mainly used in low voltage networks. Fuses are used in low voltage networks and also medium voltage networks up to 100 kilovolts. In medium and high voltage networks, overcurrent protection is mainly implemented using overcurrent relays. Overcurrent protection is also important for generators. It protects against short circuit and overloads. When a fault occurs, overcurrent protection disconnects the faulty section. To restore supply automatically, reclosing devices are often used. The measured quantity for overcurrent protection is current. Overcurrent protection operates when the current exceeds the preset pickup value. Overcurrent protection must meet several key requirements. First, selectivity. Only the smallest possible part of the network should be disconnected during a fault. Second, speed. Fault damage must remain minimal. Third, sensitivity. The protection must respond even to a small current increasement. Fourth, coverage. All network elements and the entire network must be protected. And fifth, simplicity and reliability. The protection must be easy to implement and dependable. Testing must be possible without interrupting normal operation. Overcurrent protection can operate in different ways. It can be instance, time delay with independent delay, time delay with current dependent delays. The typically time current characteristic of those protection types are shown in the diagram. Instance protection operates immediately. Independent time delay operates after a fixed delay. Dependent time delay operates faster at a higher currents. Next we examine instantaneous overcurrent protection. This protection has no intentional time delay. Its operation time depends only on the minimum technical response time of the relay and the circuit breaker. Typical operating time for instance overcurrent protection is between 5 and 100 milliseconds. Selectivity is instance protection is achieved by limiting the protection zone. The relay must operate only for faults inside its own protection area. If a fault occurs outside the protection zone, instantaneous protection must not trip. The protection zone is defined by pickup current settings. The pickup current is selected based on the maximum short circuit current at the farthest point of the protected line or element. This point determines the minimum fault current that the relay must detect. In a radial feeder with one-sided supply, fault current decreases as the fault location moves away from the source. For this reason, instantaneous protection is typically applied in radial lines, feeder supplied from one side. The pickup current is set so that all faults within the protected line causes operation. Faults beyond the protection line do not cause operation. This principle ensures selectivity without using time delay. The diagram illustrates instantaneous protection of one-sided supplied radial line. High fault current near the source, lower fault current toward the end of the line, a defined protection zone based on the pickup current. Instantaneous overcurrent protection is simple, fast, and effective. Its limitation is reduced reach in long lines or network without multiple sources. Now we look at how instantaneous overcurrent protection is set in practice. The pickup current of instantaneous protection ES must be selected carefully. The key rule is simple. The protection must not operate for faults outside its protection zone. For one-sided supply line, the most critical case is fault for the far end of the protection zone, marked as F2. To ensure selectivity, the pickup current must be higher than the maximum short circuit current at this point. For this reason, the pickup current is calculated as ES as formula, where EF2 is the maximum short circuit current at the point F2, and the second value is safety factor. The safety factor accounts for protection type, switching mode, connection through the current transformer and sensors. Typical values of the safety factor lie between 1.1 and 1.5. The protection zone can be determined in the two ways. First, graphically, fault current is plotted as a function of the distance along the line. The pickup current defines the reach of instantaneous protection. Second, analytical short circuit current is exposed as a function for distance. The protection reach is found from formula. Now we consider the line supply from both ends. In a two-sided supplied line, protection devices are installed in both ends. Fault current depends on the fault location. A fault near terminal T1 produces a higher current contribution to form T1. A fault near terminal 2 produces a higher current contribution from T2. For correct selectivity, both instantaneous protection must be used at the same pickup current. The pickup current is based on the larger of two end currents. In the example, we see that F1 is larger than F2, therefore the pickup current is set as ES as F2. As a result, two protection zones are formed from each end of the central section of the line. These zones overlap. A fault in this overlap area causes both instantaneous protection Ka1 and Ka2 to operate at the same time. This is important to note. One key point: instantaneous protection is used as a primary protection, not as backup protection. It provides very fast fault clearing but limited reach. Now we look at overcurrent protection within the independent delay. The independent time delay overcurrent protection, the operating time is set intentionally. The delay can reach from fraction of seconds up to several seconds. This type of protection is often implemented as two-stage scheme. For higher current levels, the protection may operate instantaneously. For lower fault current, it operates within a fixed time delay. Selectivity in the independent time delay overcurrent protection is achieved through time coordination. The time delays are selected so that protection devices closer to the fault operates first. The coordination process starts from the point furthest from the power source. At this point, the operating time is usually set equal to the instantaneous protection time. Moving step by step toward the source, each upstream protection is assigned a longer delay. The delay of protection stage is defined as formula, where T1 is the operating time of the downstream protection and delta T the selectivity time margin. The selectivity margin must be large enough to ensure correct operation. This means protection in zones J1 must detect the fault. It must strip and clear the fault. All this must happen before the delay of protection in zone J expires. Correct selection of the selectivity margin is critical. It must account for the delay operation time, circuit breaker operation time, and the safety margins. This coordination method creates time selectivity across the network. Independent time delay overcurrent protection is simple, reliable, and widely used, especially in radial distribution networks. Now we examine coordination between independent time delay protection and instantaneous practical in radial networks. Two diagrams shown radial feeder with several overcurrent relays labeled K1 and 2K5. Each relay has an independent time delay. The delay is increased step by step toward the power source. This creates time selectivity. If a fault occurs near motorway 1, For M2, the nearest protection Ka1 should operate first. Its operating time is the shortest. If Ka1 fails to operate, the upstream protection K2 acts as backup. Ka has the longer delay. This principle repeats further upstream with 3, 4, and 5, as shown in the diagram. The selectivity margin delta T is maintained between adjacent protections. This margin ensures that the downstream protection has time to detect and clear the fault. The upstream protection operates only if the downstream one fails. However, this approach has a drawback. Independent time delay protection results in relatively long fault clearing times for downstream faults. This increases thermal and mechanical stress on equipment. To reduce fault clearing time, independent time delay protection is combined with the instantaneous protection. In the figure, the shaded area represents instantaneous protection zones. Within these zones, faults are cleared immediately. Operation time is very short. Outside those zones, independent time delayed protection applies. Selectivity is preserved by time coordination. This two-stage scheme provides the best comparison. Fast operation for close-in faults, reliable backup protection for distant faults. Because of this, independent time delay protection combined with instantaneous protection is widely used in radial networks. This section completes the overview of the overcurrent protection. You learned that the overcurrent protection detects faults by monitoring current magnitude. It operates when the current exceeds a defined pickup value. Thank you for watching and see you next time.